Hey guys, welcome back to my channel, and this is Varun. So in the previous section, we saw some concepts relating to linear transformation such as determinants, inverse, rank and column space. Now in this section, we will touch base upon least square approximation and what it is and why it is used, and also eigenvectors and eigenvalues. So without further ado, let's start. Now in this segment, we will study least square approximation. So least square approximation is a technique which is used to find approximate solution to system of equations that do not have an exact solution. And please remember guys, this concept will be useful specifically when you study advanced regression in future sections. So note that here we will discuss just the idea of least square approximation only at high level without getting too much into math, which will be just enough so that you will know when and why it should be used. Now to understand this, let's say that we have a matrix A with a dimension of n into k. So if we have this equation Ax equals to b and we are finding a solution to this problem where we can get to b easily, then x should belong to Rk because it will have k as the number of rows in order to multiply it by a, and b should have n number of rows for a solution. Okay, so b belongs to Rn. Now if there is no solution to Ax equals to b, that means if we expand a into the column vectors, it will be a1, a2 up to ak, and x will be x1, x2 up to xk, which when multiplied should give us b. Now if we expand this further, we will get x1a1 plus x2a2 all the way up to xk ak, which when summed up should give us b. Now if there is no particular solution for this, then this will be equivalent of saying that there are no sets of weight on column vector of a where we can get to b. Or another way of saying is that there is no linear combination to the column vector of a which will be equal to b. And this is equivalent of saying that b is not in the column space of a. So let's now visualize it and understand it better. Okay, so let's say that we have a column space of a which is like denoted like this. Okay, so let's assume that this is some column space which is representing the column space of a. Okay, and as b is not in the column space of a, it will be projected not in the column space of a. Okay, so let's say that b is a vector that is going above here and it is not clearly in the column space of a. Now as we know that we can't find a solution to this, that is Ax equals to b. So this is as good as saying that there is no linear combination of a and x which can give me b. Okay, now there is no solution for this exactly, but what if we can do better or find a solution to this which is close to the original expected value? Okay, so we are now in a process of determining the closest value to the original value, which of course will not be exact to the solution but can give us the approximation to the solution. So in short, we are trying to determine an x star where Ax star is as close to b as possible. Okay, now we are in a process of finding the x star which is called as the least square estimate, and we will come to this as to why this is called as least square estimate or solution. Now let's say that we already have this, so this will be equivalent of visualizing it like this, wherein Ax star will be represented by a vector like this, and let us call it as v for now. So v is equal to Ax star. Now our objective is to minimize the length or the distance between these two, right? So this is some distance which we want to minimize, right? So in short, we are having an objective wherein we are minimizing the length of b minus Ax star, where Ax star is in the column space of a, right? Now in other words, we don't have an exact solution, but we are trying to reach the closest solution to the exact solution. Now what is the closest vector in any subspace to the vector that is not in my subspace? And it is the projection. So the closest vector will be a projection of b in CA, right? So this will be projection of b in column space of A. Now in short, Ax star will be a projection of b in column space of A, right? Now we will try and simplify this equation further. Okay, how do we do this? Basically, our objective is to minimize the distance between the projection of this vector B onto column space A and the original vector B, right? So what we do is we have to subtract B from both sides now. Okay, so AX star minus B equals to projection of B in CA minus B, right? Now when you see this term, okay, if you are familiar with the mathematics concepts and the geometry concepts, you can clearly say that AX star minus B will belong to the orthogonal column space, right? Or in short, the member of the set of vectors which are orthogonal to the column space CA. And what is that? So orthogonal to column space CA will be null space multiplied by A transpose. Or in short, AX star minus B will be equal to null space into A transpose. That is, if we multiply A transpose by this, which is AX star minus B, then we will get 0 vector. And to simplify it further, we can say A transpose into A into X star minus A transpose B will be equal to 0. And if we take this element on the right side, we will get A transpose AX star will be equal to A transpose B, right? So remember guys that our main objective was to find X star, which is the least square approximation. Now we can get this easily by this equation right here. So what we'll do is we'll bring X over the left side and send all the elements to the right side. So the final equation will become A transpose A inverse into A transpose B, which is the least square approximation. So guys, this is an important and very frequently used technique because in many real world phenomena, the matrix A is not invertible, and this is usually because it is not a square matrix, and that means that many real world systems are not represented by square matrices. We will study this further in linear regression, so don't worry about this. Now you have the system of linear equations, and can you tell me, or can you try to think about why this system is not solvable? And you have various hints with you which says solving Ax equals to B means to find a vector x which lands on B under transformation of A. You are also given the rank of A, which is 2, and the third hint is that the vector x and b are in 3D space. So please pause this video and try to think about it. The reason this system is not solvable is that matrix A has a rank of 2 as mentioned in the hints, and therefore the matrix A squishes the 3D space onto a 2D plane. The problem is that the vector Ax lies on the 2D plane like all the vectors that get multiplied by A, but vector B does not lie on that plane, and hence this problem is unsolvable. And we often come across such systems of equation in real worlds also, and here we want to find the approximate solution for them. That is, we want to find the vector x which comes as close to B as possible after the transformation of A. And it is here that you will apply the least square approximation to get the answer. Now we will study what are eigenvectors and eigenvalues. So eigenvectors occur in many linear algebra problems, and we will use these concepts heavily in popular machine learning techniques such as principal component analysis. Now in this section we will understand these concepts intuitively and learn how to compute them manually and in NumPy. So to give you a gist, eigenvectors of a matrix A are special vectors which do not change their direction or span under the transformation of A. They just get scaled in the same direction, and the magnitude by which they get scaled is called eigenvalue of that eigenvector. And if the vector reverses its direction, the eigenvalue is negative. And mathematically this can be represented by the equation AV equals to lambda V, where V is the eigenvector of the matrix A and lambda is the eigenvalue. So you can understand this with the help of example. So you can say that points of x-axis and diagonal lines do not change their spans when stretched out during the transformation, and therefore those will become the eigenvectors of the transformation, and they thus only change the magnitude. Now let's solve this equation intuitively so that we can come to a conclusion how to derive eigenvectors and eigenvalues, right? So we have this equation AV equals to lambda V. So wherever we are scaling V, right, and V is a matrix, so scaling by lambda would mean we are multiplying the matrix lambda 0 0 0 lambda 0 and 0 0 lambda by V, right? But we can also say it like this, lambda into identity matrix, right? So this equation we'll try to replace it by an identity solution. So AV equals to lambda I into V, right? Now if I bring this element to the left side, the equation will become AV minus lambda I into V equals to 0, or simply saying A minus lambda I into V equals to 0. Now we will be looking for a non-zero solution of V, which is the eigenvector in our case, right? So we are looking for a non-zero solution for it, right? And this matrix right here will look something like this, right? So this is just an example. It will look something like this. Now the only way a matrix vector multiplication is 0 is when the matrix squishes the space into lower dimensional, right? And this we have studied in the previous sections also. Now this means that the determinant of the matrix is 0 in that case. So thus we can say that the determinant of A minus lambda I is 0, and this will actually do a squishification to lower dimension. Now we'll take an example to solve this. So let's say that we have a matrix A and we are solving the determinant for it, right? So the matrix is 3 minus lambda 1 and 0 2 minus lambda. Okay, now the determinant of it will become 3 minus lambda into 2 minus lambda minus 1 into 0. And if the determinant here is 0, then we can safely say that 3 minus lambda 2 minus lambda equals to 0, and hence lambda equals to 2 or lambda equals to 3. So what we have done is, here we have subtracted lambda from the diagonals and calculated the determinants, which is equal to 0, and then derived lambda from it. Now when this is shared, that is when we have a determinant of 1 1 0 1, okay, which will be 0, and we have to calculate the eigenvalues. What we'll do is, again we will subtract lambda from it. So 1 minus lambda from the diagonal, and then the multiplication of 1 minus lambda into 1 minus lambda will be 0, and therefore lambda will be 1. So we can safely say that, so the eigenvectors will have eigenvalues 1. So if it is a diagonal matrix, then we can always say that the values in the diagonal are eigenvalues for each of the column vector. Now if you have understood how eigenvectors and eigenvalues behave, can you solve these questions for me? So the first question read as the eigenvector for transformation A, and you have to choose among these given options. And the second question is the eigenvalues for the transformation A, and then you have several other options for this second question. So please pause this video and try to solve these questions. Now in the first question, the transformation scales the vectors on the x-axis to 2x and those on the y-axis to 5x, as we can see in the diagonal values. Okay, thus the vectors I hat and j hat will become the eigenvectors. So what are I hat and j hat? They are 1, 0 and 0, 1. And in the second question, the transformation scales the vector on the x-axis to 2x and those on the y-axis to 5x. So in this case, it will be 2 and 5. Now we will continue our learnings on eigenvectors and eigenvalues in the next session too. But before concluding, let's summarize our learning so far. So we have seen that in the equation AV equals to lambda V, V represents the eigenvector and lambda represents the eigenvalue. Okay, and we can shorten it up further so that we'll get the final equation as A minus lambda I V equals to 0. And the only way a matrix vector multiplication is 0 is when matrix squishes the space into lower dimensional one. So this means that determinant of the matrix will be 0, and thus we'll get the equation determinant of A minus lambda I is 0, right? And to find the eigenvalues and eigenvector of this matrix will involve finding the eigenvalue lambda by solving the equation determinant of A minus lambda I equals to 0, and using the lambda values or the eigenvalues found in step 1, we will solve the ultimate equation, which is AV equals to lambda V, to find the eigenvectors of it. So that will be all for today, guys. I will be continuing our learnings with eigenvectors and eigenvalues in the next session too, along with the NumPy implementation of it. Until then, guys, do let me know in the comment section how are you finding the content so far, and please do support by subscribing my channel if you haven't done it already, and liking the videos if you think that these material is helpful. I will be starting the machine learning series soon, so stay tuned on this channel. And to get the latest updates, please don't forget to hit the bell icon. I will be seeing you soon in the next session. Until then, keep learning and inspiring others. Thanks and take care.